Good afternoon. Welcome to this special seminar. Today we have Dr. Franklin from MIT Haystack Observatory visiting us, and Frank and I, and also a few colleagues, were working on a research project to build a radio interferometer to study lightning. And Frank is really a radio instrumentation expert, and he helps us designing and also implementing the instrument. And Frank is also working on a lot of other projects. And one of those projects is AERO-VISTA, and this is a satellite radio interferometer project. And I heard, so we meet like every other week, and I heard a lot about this name. So I'm really curious what he will tell us about this. Thanks, Frank.
Thank you very much. It's a pleasure to be here today. We had a good morning. We actually got everything to work 100%, so that doesn't always happen with experimental stuff. I'm Frank Lynn. I'm from MIT Haystack Observatory. I've been with the observatory almost 23 years now, since I finished my PhD from the University of Washington. My background's in space plasma physics and radar remote sensing, and I branched out into astronomy and other things lately. But AERO-VISTA is a really interesting mission. It started actually as AERO, which was a H-tide submission to NASA Heliophysics SMD for a small satellite. And then we had kind of the gumption the next year to put in a technology demo application for VISTA, which is to do interferometric radio imaging and space demonstration. And they kind of lumped it all together and it became one project, AERO-VISTA. And unfortunately, heliophysics budgets are tight, and we were just told that we're going to have about a year gap before they can finish to fund us to orbit. But we're at flight model hardware now for most things, and I'll go through, talk about the mission, talk about what our science goals are. I put a little extra more science in here than I normally do because I know the physics people here are going to be interested in it. And then you'll see a bunch of the hardware and a few of the videos, and there's a lot of backup slides for questions. So, all right, let's see if I can get this to advance here. Is it gonna? No? There we go. So we have a big project team for AERO-VISTA. MIT Haystack Observatory is the PI institution. Phil Erickson is the PI of AERO. I'm the PI of VISTA, and together we manage this project with Mary Knapp, who's our assistant project manager and PI, and Becky Masterson, who's from AeroAstro at MIT campus, who's our project manager. We're at Haystack have been in charge of the instrument science, the architecture. We're doing all the payload software, signal processing, ground processing, and we're doing system integration and test. We've been intimately involved with MIT Lincoln Laboratory, and I've worked with them for the last 3 years developing the vector sensor payload, which is a very unique radio instrument by itself, and doing several of these in space deployable makes it for a very challenging instrument, and it's proven to be expensive and challenging as it turns out, but we've made tremendous progress. The group there that we're working with is a group called Group 86, which is the Advanced RF Technology Group. So they get the RF problems nobody else wants to solve, kind of. MIT AeroAstro has been involved with this. We've got a lot of students, graduate students have been working with us. It's been an absolutely fantastic project for students. We gave them something to build originally, other than doing some systems engineering, which was what we called the auxiliary sensor package. It turns out to be actually kind of fundamental to the success of the mission, but we never should have called it auxiliary because NASA kept wanting to kick it off the spacecraft because it was called auxiliary. But nevertheless, we called it the awesome sensor package, I think is what it really should be called, because it's turned out really great and the students have done an awesome job on it. But we also have the Space Systems Labs, which is another part of AeroAstro, where our project manager is from, and she's been doing system engineering and INT support. And we brought in some students for thermal analysis in addition to people from Lincoln Laboratory. Another partner we have is Morehead State University. They've been handling the bus procurement. They've got one of the ground stations and mission operations centers at Morehead State that we're using. And they're in Kentucky, but they've got this beautiful facility and lots of really great people to work with. And so we've worked closely with them on electromagnetic interference testing and bus selection and communications. And then we got a science team that's not just MIT Haystack. Jim LaBelle at Dartmouth is our science lead and has been, his focus is on auroral radio physics and emissions and plasma physics behind it. And we got Juha Viernen at the University of Tromsø is going to be helping us with ground assets in Scandinavia for the mission. And we had Merrimack College, but where Alan Weatherwax was, who's also on our science team, but he's actually recently joined Haystack. So he finished up being a dean, I guess it was, and he had to have a life change, and his life change was to go back to doing science.
I know, all the way back from the University of Maryland.
Absolutely, absolutely. He's a great guy. So this is the structure of the team. There's lots of people with multiple roles. We made Phil kind of the overall AERO-VISTA PI. I'm the VISTA PI for technology, and he's the AERO PI for science. It all looks very complicated. In practice, we work together very nicely. We all report to Heliophysics SMD on this one. And then there's the science team. We have people at MIT Lincoln Laboratory who are on the science team who are more interested in the sensor technology than in the radio science and auroral and space physics. And then, we've got a whole bunch of people doing different roles, building stuff, but we've had just, I bet there have been 75 people working on this project in various times and places, and lots of students have cycled through, lots of summer students, and it's really been a fantastic program for Haystack. So our target is the radio aurora. So this is optical from the International Space Station, taken in 2011. One of the astronauts that went up liked to take all kinds of photos of everything. And he got these beautiful movies. And this is, from the International Space Station during a geomagnetic event. The auroral oval is expanded down to mid-latitudes, and now you've got these auroral arcs, and you can see all the structure here. This is in the optical. The radio structure has a tremendous amount of emissions. It should have characteristics that look very similar, but different because of propagation in different ways. And we want to measure them. We want to actually be able to image radio aurora and be able to go up and understand, well, not only do we see this radio emission, but where is it coming from? And what does that tell us about the source regions? And what does that tell us about, how compact the source region is? If there's a maser involved, what's that telling us about the instability that's being excited, et cetera? So underneath it, that's the big picture is you can do this optically. Why can't you do it in radio waves? And many of the phenomena we're interested in have been known about for a long time, but understanding them has been something that's had kind of sporadic progress. There's been a lot of modeling progress, I'd say, but the constraint of the modeling versus what's really happening physically has been somewhat limited. So one of our key observables we're interested in is auroral kilometric radio emission. This is really going to be the strongest thing we see. And auroral kilometric radiation occurs usually several thousand kilometers out from the Earth. The actual source region is not well constrained, and it does vary in position. That source region, we can observe it with satellites that are out beyond this region. Older ones like the Viking spacecraft. You had GeoTail, which was way out in the magnetosphere, way out in the tail. And it typically is emitting frequencies that are in the few hundred kilohertz to a little under a megahertz range. They're very dynamic in time. If you do an audio thing, which might work, okay, oh, it is working. So it is the sounds of space from the 60s, okay? So people went up and measured this, and it became science fiction movies. But if you convert these signals into an audio range and listen to them, there's all kinds of variability. And what's going on underneath it, that's enough of that. I can only take so much of this. Okay, we're gonna make audio bit. Hold on here. Stop that. Okay, that's enough of that. Underneath it, electron density, electron temperature, the propagation of the signal to you is all influencing what's there. There are harmonics of signals. The signals, though, this is a time frequency spectrogram. You've got frequency on the vertical, time on the horizontal. You listened to it. You got a visceral feel for what's going on. But underneath it, there's a fundamental thing missing from this, which is, where is it? Is it there? Is it there? And people kind of have an idea because the spacecraft are flying by, and there's been some attempts to triangulate things, but nobody has really gone up and said, it's there and we're following it, or it's a source region and there's 3 emission regions. And so we're really wanting to be able to do that at these low frequencies. Now the challenge is that, AERO-VISTA, we're going to be observing, it turns out, from about 250 megahertz up to about 15 megahertz. These are wavelengths that are very, very large. And traditional radio interferometry systems would be spaced at half a wavelength. So if you had that at 30 meters, say, you'd have 15-meter spacing between your spacecraft, which is like a constellation mission of great and terrible proportions. And no one wants to try to fly stuff like that too often. I think I think some of the defense contractors are doing stuff like that, but it's very expensive and hard. So underneath it, we wanted to ask, was there a technological way to get around that requirement? And that's where we got into the types of sensors that we chose to use for this, called electromagnetic vector sensors. And I'll get to those in a little bit. We have some very fundamental science questions. One of them for AKR that's probably one of our most important ones is, how does AKR get to the ground? We see these radio signals. They can be at most, say, 750 kilohertz. And yet, they're happening thousands of kilometers out. The radio signals are propagating out from that. Most of the energy is going away into space, away from the Earth, and it makes Earth visible out in the cosmos. And yet, kind of the back lobe of that radiation is coming towards Earth. And yet, if we just take like ionospheric physics, we say, well, there's a plasma frequency, there's refraction, and the plasma frequency, even in the polar ionosphere and the dead of night, never really goes below, at the very minimum, about a megahertz. And so these signals just should be refracted and never get to the ground. There really shouldn't be too many paths that allow them to get down. And yet, there are spacecraft observations combined with ground-based observations at the South Pole, for example, that clearly show that you see events and some of the signals do get to the ground. And so there's this fundamental question about, well, how are they getting there? What is the mode of propagation? Is it along the magnetic field line? Are things bouncing around and then somehow wiggling down? And we're hoping with AERO-VISTA to get towards some of the answers on this. Now, hopefully we'll answer it, but at the very least, we're going to be able to tell things about where the radio signals are coming from with this kind of radio technology. There are other types of auroral emissions. So I mentioned AKR. We've got all these kind of wonderful questions about it. It's got certain polarization. It's got certain characteristics. Other things show up in the auroral measurements that are made at South Pole Station and in the Arctic at a variety of stations. Auroral hiss is one of them. This is a low frequency signature that's below the electron cyclotron frequency. It's got all kinds of dynamics. There's everybody's got ideas about where it's coming from and so forth. It's not well understood. Auroral roar may be some sort of harmonic of the electron cyclotron frequency, but with some nonlinear mode conversion that changes the way the radio waves are propagating. Medium frequency burst is at a higher frequency range. And this, often, may be related to kind of early arrival of substorms. And there's a real question about the generation mechanism. And so the other thing about these is, you'll observe these at a fundamental frequency, like 200 kilohertz. Often the harmonics will be present. Sometimes the harmonics will be filtered and we don't see them. And so that actually is telling you things either about the propagation environment between you and the source region, or about the source region itself and what it's doing to the harmonic energy that should be created often. Just as an example of that, here's some ground-based observations Al Weatherwax and Jim Lovell took back in 1995 up in the Arctic. And you have frequency now on the horizontal. This is a little different scale. Before we were looking a few hundred kilohertz that was down in here, where AKR runs around down in here. Now we're up to 5 megahertz. And you can see versus time, you can get, this is on the ground, so there's AM radio broadcast stations. The color intensity is the strength of the signals. And then you have this thing, the arrows pointing towards aurora. You see these medium frequency bursts. When you look at this on time frequency spectrograms, it's just superimposed. You might have multiple sites. You might be using timing to try to figure out where things are. But this level of being able to do any kind of direction finding isn't there. So you don't really know where things are coming from. And often it's very important. Once you're down in the ionosphere, you've got a lot of refraction going on. So at altitudes down 200 kilometers, 100 kilometers or below, any radio signal we're seeing on the ground has actually been bent around a lot before it gets to us. And that's something that when we go up to LEO, we get rid of most of that. And we'll hopefully be seeing much more direct paths. They'll still have refraction, but it'll be much more predictable. So the mission. So we've got 2 6U CubeSats we're building. They're going to go into a sun-synchronous polar orbit above the ionospheric peak. We're going to be between probably 400 and 600 kilometers. We don't have our launch yet. They're going to be launched at the same time from the same dispenser. We have to control the relative delta V between them as they go out. So one can't go out real fast and then the other slowly. They have to go out relatively close together at pretty much the same cross-track velocity. And then they're going to, once we bring them online and they unfold their solar panels and start to maneuver themselves with reaction wheels, we're going to be able to do drag positioning. So we put one of them, say, in the ram direction where its profile is slower. One in the drag direction that'll pull them apart, if you flip that, you can cause them to come back together and to try to keep these spacecraft within about 100 kilometers for most of the mission. If they get out, there's a revisit time, and it takes a while for them to come together, and then you can keep them close to each other again. The technology we're doing is a deployable antenna that's going to fit in the 6-cube CubeSat. In fact, it does, and I'll show some movies of it in a little bit. And this is what's called an electromagnetic vector sensor, which is a really interesting radio antenna technology. It's really kind of 6 elements in one, and I'll get to it in a second. And we're packing that all into a 10 centimeter by 10 centimeter cube, and it pops out. And across this is about 4 meters across once it pops out. So it's kind of the size of this room almost, or the size of the table actually, when this thing pops out. And then there's a monopole that pops up a couple meters above the spacecraft, and then every last inch of the spacecraft is filled with stuff. And underneath it, this antenna is really unique because it allows us not just to get those time frequency spectrograms, but to, in a method I'll discuss in a minute, measure the direction of arrival of the auroral radio signals. We're also going to do an RFI survey that's kind of, let's see what we see and keep track of it as we orbit, and turn on our instrument occasionally and take data in various places we wouldn't. NASA actually wanted an RFI survey, so this was to serve that purpose. But underneath it, it let me push the specs of the instrument up a little bit to give us some discovery space, right? I can say we want to go after these auroral emissions, and everyone was saying cut the instrument off at 5 megahertz, and I was like, no. I want to go to 15 megahertz so I can see stuff that we're not expecting. And they don't like that because that's like discovery science, and you can't propose discovery science, kids. I'm sorry, but nevertheless, I wanted that measurement space available. If we see something interesting, we can do something about it. Now, it turns out for the interferometry demonstration we want to do on orbit, we're going to be taking these 2 satellites, collecting data, raw data on both of them, bringing a little bit of the raw data to the ground in order to show that they're acting like an interferometer when we do the processing. Now, it turns out that I like to do controlled experiments as an experimentalist, so I wanted to have ground beacons that I could control and turn on and turn off, and be absolutely sure with the code I put on them that they're really the signal I think they are, and that when I demonstrate the interferometry, I can predict exactly what I expect to see. So to do that, I want to be above the ionosphere cutoff, which means I wanted to be up in the 13, 14, 15 megahertz range. So that's at the upper end of the band for this. And then, the other thing we're hoping to be able to do, and I've got a PhD student at campus who's in AERO-VISTA who's working on this. She's working on the algorithms and techniques that we need mathematically to use these sensors in order to make images. Some of the imaging comes from the sensors themselves, some comes from the baseline between the 2 spacecraft, and some of it actually comes from the motion of the spacecraft, giving us different look directions on an emission source that might be constant long enough that we can kind of make a picture of it. And that kind of blurs things out probably, but it'll also give us kind of there's the spatial blob as you passed by it that was emitting these radio waves we're interested in. So electromagnetic vector sensors. This is a really interesting technology. It was developed in the 1990s and people tried it and it didn't work. And it didn't work for reasons we actually figured out and some others figured out a while ago. It's actually hard to build these antennas. What they are is, if you think about it at some level, is they are 3 loops orthogonal to each other, 3 dipoles orthogonal to each other. But you make the dipoles and the loops sensitive to the same frequency range, and you arrange them so that their phase center of the electromagnetic waves they measure are all at the same point roughly in the spacecraft or in the antenna. And what that does is it allows you to measure the 3E or 3 electric field components and the 3B or H field components of an electromagnetic wave. And underneath that, when you do that little bit of magic in a narrowband frequency range, that gives you E cross B, which gives you the pointing vector. So all of a sudden, at a fundamental level, you've got a sensor that measures the K direction that the radio wave is propagating in. And so that actually is really interesting because normal antennas that are put up on these spacecraft are often dipoles or maybe a loop antenna. They don't have this vector capability. Sometimes there's electric field probes that really people do try to go to a lot of trouble to get all the E field components, for example, but often the frequency range they can do that in is a very low one. And part of how we do this for this wider frequency range is we make these antennas electrically small. So a 4-meter antenna over most of the frequency range I talked about is actually an electrically small antenna. And it turns out that although they become less sensitive at some level, they also become extremely predictable in how they're behaving as a function of frequency. And then the other aspect of this is we actually have ways of making what's called an active antenna, where we don't actually sacrifice a whole lot of signal to noise ratio, even though the antenna is becoming small and inefficient. And so this allows us in a single sensor to do spatially resolved imaging. And it turns out that, the kind of first order thing you do is you just kind of look at the E and the BE and you get the energy and you compute a cross product and there's a pointing direction on a radio wave. It turns out that when you start looking at the statistical distributions of the energy coming into the different elements, you can cross-correlate all the energy from the different elements and understand how that energy is varying across the elements of the array that form this vector sensor. And it turns out that by doing that, you're kind of able to actually, you can think about it as like staring nulls at the sources and figuring out, well, the nulls null the sources best. Or you can think of it as, the underlying technique in EE speak that they talk about is that you're computing with something they call the array manifold, which is basically how do you steer the energy by summing all these elements together dynamically in order to maximize the energy you want in a given direction. And when you do that, it turns out there's a lot of additional degrees of freedom that let you image and locate multiple sources. So all of a sudden, you don't just tell that one radio wave is going there. You could do something really neat. You could say, well, there's a radio wave coming up at me, and there's a radio wave coming down at me, and they're going like this. So we'll be able to actually do things like that on orbit, and it's going to be very exciting in that not only can we tell that, say, a radio wave is propagating and the direction kind of coarsely where it's going. Usually, first order statistics gets you a few degrees. Second order statistics gets you about a degree. If you go to third order statistics, you can get to about 1/10 of a degree with a single sensor. So a single 6-element antenna that's electrically small is going, hey, that's the direction to that radio wave came from. Now, when we combine that into interferometric arrays where we take multiple platforms and do this, you actually can use the long baseline to get very fine angular resolution. We can get another order of magnitude performance in our imaging resolution. There's another thing you can do with these that's pretty neat, that's very relevant for future satellite missions that we're going to demonstrate, which is these sensors can use those degrees of freedom. Instead of to localize something, we can drop a null on something. So we can null out, say, strong radio frequency interference from one direction to let us distinguish something that might be weaker that we're interested in scientifically. All right. Now, go ahead.
So why aren't we using these more on the ground, like with what we're doing with Lightning?
They're new. Most people don't know how to build them. There was about 10 years where people thought they didn't work because they built them wrong. And I'm going to have 10 elements out on 50 to 200 kilometer baselines here in about a year on the ground for another project. I was just talking to Ningyu about using them to look at lightning. So yes, the answer is we can, and they'll be very interesting sensors for it. All right. And we should just be able to collect the data in the not too distant future. So modes of vector sensor modes. So this is an illustration showing the antenna pattern simulations for the AERO-VISTA spacecraft. This is showing kind of the EX measurement and the portions of that antenna. That antenna that goes out, they're the tape springs, and they come out and they've got wires on them. And we actually treat the wires not like just a dipole. We actually bring them in to what we call a mode former, and we treat them as differential antennas, and we actually amplify them differentially, and then we combine the energy in different ways depending on what field component we're trying to measure. So like when we measure the field across between these two elements, we get an EX measurement. That has a corresponding dipole-like pattern if we built our spacecraft right and built our antenna right. EY is of course on the orthogonal direction. EZ here is the monopole, okay? So that's because of the logistics of deploying out of a spacecraft, we didn't do a dipole for this one. We use a monopole and use the spacecraft body to create kind of an image plane for that EZ measurement. Now, oops, what did I just do? I don't know what I just did. I stepped on something in advance. That was cool. Okay, so now, say this EX measurement. I'm going to use these same elements that I use to measure EX, but I'm going to measure the current that goes around them in the loop. Now I've got a loop antenna. I'm going to have that loop antenna is going to have a loop antenna response. It's orthogonal, as you can see, to the dipole antenna response, because we want that to happen, right? We want to be able to measure E and B, and we know E and B in an electromagnetic wave are orthogonal to each other. And so by doing that, we measure all these things, and then finally we have a perimeter loop around the outside that goes all the way around the outside that gets at that HZ component. All right, and one of the challenges we've run into is that in practice in the spacecraft, we couldn't tune the loop areas quite right, so we have some sensitivity differences, but it turns out the algorithms are fairly insensitive to that in general. So for the range of signals we can see efficiently with the system, we actually are meeting our sensitivity requirements, which I'll talk about for the mission, just because we combine the information together to make the measurement. Now, of course, if you have a electromagnetic wave and it's got an EX, for example, and it's polarized as EX into your antenna, your EY and your EZ aren't going to directly see that, for example, but your orthogonal HY component will probably see that. So I got E cross P right for that. So this is underneath it. If you think about it, when I talk about measuring the correlations between these, it's like I have an electromagnetic wave come in on one of these patterns around that's a dipole pattern, and I'm measuring how much the energy varies in that electromagnetic pattern on the dipole versus how much it is in loop B or loop A. And by understanding that covariance matrix that results, we get the information necessary to do this imaging. Beamforming. This is an example of taking 6 of those modes, adding them together with the correct phasing for a particular direction, and creating a null in one direction and a beam in the other. So this would be a very conventional way of just taking the energy from the sensor, adding it up, and trying to emphasize one direction, very broad beam, not a lot of angular resolution. But you'll notice that the null in back here is actually quite sharp. And that's actually one of the things that is when we're forming this matrix of information that we're using, the covariance matrix, it's actually the null, the variation towards the nulls that is giving us a lot of information about the actual directions of the signals we're looking at. Now, you can extend that out to imaging. This is an example of a ground-based sensor called HF-GEO. It's a different kind of vector sensor from the AERO-VISTA one. You'll notice this one looks much more conventional. There's 3 orthogonal loops and there's 3 orthogonal dipoles, quite literally. It turns out these are very hard sensors to make this way. The one we made is a lot easier to make because it's the differential version of this. And differential systems often, and when you're doing experimental work, you can cancel common mode noises in systems, and it's very valuable to be able to do that. And this was some collects that were done by AERO, which is a US government agency, to look at the spatial distribution of energy propagating through the ionosphere. And we actually have very narrow Doppler shift right here. This is range, so it was a radar-like measurement. And this little source right here, they picked it out with the vector sensor, and they mapped the energy in azimuth versus elevation. And this is like a vertically polarized wave propagating on the ground, along the ground, and it's showing you kind of the energy distribution that the sensor has there. So these the vector sensors have many degrees of freedom. What we do to do the analysis often looks like a constrained sparse inverse analysis where we have a model and we wanting to fit model parameters such as the angles of arrival, the amplitudes, versus the measurements, and the measurements are that covariance matrix where we've compared every element to every other element in itself. Currently I'm on a timer or something, I probably should be. But an example down on the right, we measured WWV, which is a radio signal at 15 megahertz. That's a time signal with a vector sensor I'm not showing here called ATOM at Haystack, and we actually could pin a given direction over the horizon with pretty good SNR on that signal, and it's one narrowband signal, but. So there's a lot of subtleties in this. There's some papers if people are really interested, but vector sensors are very powerful technology. Now, when you combine them in interferometric arrays, you start to get some interesting things happening. A normal radio interferometer, if I want to have a wide field of view, I have to have a couple antennas spaced, say, at half the wavelength. That's going to allow me to understand at a very wide angle where something is coming from. If I want fine angular resolution, I want to make the distance between those antennas get bigger and bigger compared to the wavelength. Now, when I do that, that gets me very fine resolution, but I all of a sudden have ambiguity. I don't know whether that fine resolution is there or there or there, so I lose that big picture. Now, on the ground, what we do is we add short and long baselines, and all of a sudden we can de-ambiguate that interferometric measurement. Underneath it is a phase measurement. What we're really measuring is the phase of the radio wave or the phase and time delay of the radio wave as it moves across a set of antennas. Now, this allows us to obtain angular resolution, and often astronomers call these things fringes, but they're really ambiguities in your ability to estimate the direction of energy in a radio wave. Now, with vector sensors, we have a very interesting thing. We have a compact antenna that I just told you gives us angular resolution on the order of, a degree, a tenth of a degree, a few degrees. Well, all of a sudden, that's acting like two antennas that are close together. If I put two vector sensors apart, they each know coarsely where the radio signal is coming from, and the intercomparison between the two sensors gives us fine angular resolution on the target. And so all of a sudden, we break those ambiguities with the vector sensor, and we don't need the short baselines. Now in space, that's really important, because say I wanted a system that needed 10 or 20 kilometer baselines for high resolution, but my wide field of view might take tens of meters, a few meters. All of a sudden I have a very difficult problem. I have either a spacecraft with multiple antennas on a boom, or I have to fly spacecraft together in a constellation close together. That's all very difficult. On the other hand, if I should just loft two spacecraft and have them the 10 kilometers apart, but they still know this coarse angular information, then now I actually don't need those short baselines in my constellation. I just need enough sensors to get the sensitivity that I need in the overall system. And so this acts like additional degrees of freedom. The vector sensors also can do full polarimetric estimation, which is really interesting. Or you can use kind of redundant information to improve your estimation variances. So how well can I determine, say, the angle or the amplitude of the radio signal? So the mathematical development for this is complex. We've got it ongoing. I'll talk a little bit about the special considerations in the plasma environment. It turns out dipole antennas in space plasmas don't behave like dipole antennas in our atmosphere here or on the ground. There's some very interesting plasma physics interactions in these radio frequency ranges we have to be aware of, at least. But so this is underneath it, is that it lets us build space constellations of radio interferometers that take fewer sensors and that don't need sensors that are close together in the architecture. And that makes them much more achievable in the kinds of technology we have for building space platforms today. Now, how are we going to deploy this thing? So the first thing, we have to cram it in 6U. We thought we could do it in 3U, and we were wrong. Boy, were we wrong. I look at how full the spacecraft is, and I can't believe we ever thought we could into 3U. So it starts all packed together in a small spacecraft. The spacecraft is unfolded its solar panels, so it's got a lot of energy. Then there's a point after some period of time that in the ground in the loop, we're going to pop it up. We actually have some little cameras on each side I'll talk about called eCams that have wide field of view. They're fish eyes. So we'll see it pop up. Okay, all going well, all our other sensors say it pops up. Then there's a point where there's doors on here that come open, and this is a spooling mechanism, and the whole thing goes out. Now, it doesn't actually, it turns out everybody thinks it goes real fast. After it's been stored on the launch pad for however many months, it doesn't go very fast. It actually goes, and it takes about 3 days to get all the way out. And if it gets stuck, we're going to have to model it and deal with it. But it doesn't seem so far to get stuck when we did our creep testing. It actually, everybody who was designing this and talking to us, and all our motion control, attitude control people were like, oh, how much big is the impulse and how hard is it? You know, it's like a ballerina, but right, or an ice dancer or something. They pull their arms in and they go faster, right? Here we're popping our arms out. We're going to go slower. So our angular momentum is going to slow down. And we're doing it actually really slowly. So it turns out like all the things we thought would be sharp impulses to the attitude control system are all these slow, gradual things that, you know, the tracking loops and the ACS can actually track. Then what we do at the final thing is we pop a little door open here at the top, and it pops out the monopole, and the monopole goes and unfolds. Now, a lot of this stuff is all tuned to work in 0G. So on the ground, we either have to have gravity offload, or like the monopole, we deploy upside down sometimes. And and there's a tension between, well, if we made it have enough spring to go up on the ground, is it going to damage itself or get stuck when it's in orbit? But I'll show you some of this in a second here. So let's look at this. This is the loop deployment on a jig. So this is a gravity offload jig. The loops are in the center of the spooling mechanism. And let's see if I can get it to go. All right. This one actually, gravity, you'll notice this got hung up here, and then it finally went. The springs had enough force to put it out. And these were new springs, so it was a little faster. But you can see them. Now on here, you can see little pieces of Kapton tape. This actually has a wire. These tape springs have a wire on them that is the antenna itself. And if we had more money and budget in like another project, we would embed them in the tape springs themselves. But that didn't happen for a variety of reasons. All right, that's enough of that one. let's go over to this one. This is the monopole deploying down here. So, and I never understood how much mechanical complexity was in all of this. We thought this was easy. This all stuff was all easy. And it turns out it's probably one of the technically harder parts of the mission. So that was great. It popped up down. Now later I'm going to show you one against gravity, and you're going to see the door pop open. All right. So let's see here. These are good. So now we took all that prototype stuff. We ended up building one. And the first time we did it, nothing happened. It didn't. We put in the spacecraft, the engineering model, we put everything in, and we pressed the button, and nothing. And that was very disappointing. And it took us another, I don't know, almost a year and a Delta model later to get to this is a fully integrated engineering model. It's got our radios, it's got the antenna, it's got what we call the auxiliary sensor package, or the awesome sensor package, the ASP. It's all integrated. It's actually being controlled by the bus. And we're sitting there with the commands and telling it to turn on the deployers. There's little pin pullers in here that get fired that open the various stages. So this is the pop-up stage. And they're slow-mo. They had to do slow-mo on that. So that popped up, and that's got exactly the gravity offload to offset the thing and kind of keep it in balance. I personally want more spring force, but the mechanical engineers keep telling me that I shouldn't do that because I like it just to pop up. But next is the unspooling. Now we tape it in here in this jig. We don't want it going. We have no gravity offload frame, so we tape it so it only goes a little bit of the way on here. So it doesn't. We don't let it unspool on this one. The unspooling was the other test. And then finally, here's the one that's I always tell this one I wanted them to do it upside down, but they didn't do it. But there's the door. So it'll unspool if you let it unspool. So we often Kapton tape these things to hold them when we're in between. But in any case, this all got integrated. This was part of the reason our project was a little higher on the budget than we'd hoped. Oops, there we go. Antenna performance. So we're not just trying to build, the mechanical thing of this. We want this to be an antenna that is electromagnetically what we want. And when we started to simulate and model and compare the data that we were taking, we found out that like our loop component, in particular these cross loops, needed to be double their size really. And so we're going to live with that for the mission. What I'm showing here is the sensitivity that we need with our target for the overall mission. The auroral emissions are shown as these boxes of various colors here. So there's in some range, the stronger emissions get seen by those loop modes. The weaker things will be the perimeter loop and the dipole. Now it turns out the algorithms are very robust to about -15 to 20 dB SNR. So it doesn't actually, when we do this joint simulations of processing, we put in all these sensitivity effects, and what we find out is that the sensor picks out the direction anyway. Does it do better when the SNR is higher? Oh yeah, it does better when the SNR is higher. But nevertheless, for cramming this in all small spacecraft, we were pretty happy that everything got in the right range, and the aggregate sensitivity of all the elements ends up meeting our target. We've looked at the rates that these are going to happen. We're, as it turns out, going to be launching into kind of solar maximum, and we should actually, and it should take us 30 or 40 days of data collection to get to a complete event set that we set for our science requirements. So the antenna and the modeling and the measurements of the antennas have come out right on top of each other. Now I mentioned the plasma effects that are really interesting. So it turns out dipoles in space plasmas in frequency ranges that are kind of between the plasma frequency, the cyclotron frequency, and the upper and lower hybrid frequencies don't actually behave like a dipole in free space would, or a dipole at a higher frequency range out in a plasma where you're far away from those plasma physics parameters and frequencies. And so it turns out that there's a region, there are different regions for this antenna where it sees different impedances. So in an impedance in an antenna, a perfect antenna, I want to match the impedance of the antenna into the impedance of the sensor that's measuring the antenna. And I want maximum energy transfer. That's the usual way you try to maximize signal noise ratio. Electrically small antennas, often what you do is you actually use an amplifier that matches the antenna well and maintains the ratio of the energy and the noise in the sensor, but may not be a resonant match. Now it gets worse here because what we actually have is an antenna that as it flies through space, sees different electron density, different magnetic fields, different temperatures, different orientations to the magnetic field. And in some of our critical frequency range, there's actually, energy. And some of that energy looks like noise to us, but they're plasma waves. So one person's noise is another person's science, of course. Some of it just looks like, the sensor is less sensitive from the point of view of seeing things distantly. So we had to look at this and model this, and this is a model that I did with John Sabota at MIT Haystack Observatory. And we swept this model over a simulated orbit. I used a thing called RISAT-1 as my TLE for this. But we had a student work with us to combine that with our antenna sensitivity model, and this is what we got. So here we have time. This is only part of an orbit. It's like 10% of an orbit. We have frequency here, which is the measurement frequency. We're actually showing on the top the resistance of the antenna, or the real impedance. We have the imaginary impedance or reactance of the antenna. This corresponds to loss. This corresponds to phase shift. And what we see is actually there's a region that's between the electron cyclotron frequency and the upper hybrid frequency, which is the combination of the cyclotron and the plasma frequency. We actually have a region where we have quite a bit of phase variation. There's a narrower region between the cyclotron frequency and the upper hybrid frequency, or the plasma frequency and the upper hybrid frequency, that is a resistively lossy region. And then there's another region down below that we're resistively lossy, but we actually match it pretty well. And so what happens if you map this into a sensitivity model of the antenna is we end up with this stripe kind of that varies as a function of orbit. And this variation is purely the model we used. Okay, so it's sweeping around the Earth with an ionospheric model saying electron density is this, next position, electron density has changed, it's gone up, it's gone down. So the real sweeps will be physical, based on what we're passing through with the spacecraft. But we actually have a region where we actually maintain our sensitivity. We have this region where we lose sensitivity, and then there's this gradual region where we start insensitive and become more sensitive. And interestingly, this is 0 degrees to the magnetic field for the radio wave. This is 87 degrees, so perpendicular. You can actually see mode splitting down here perpendicular. So we actually end up with sensitivity that is mapped out in plasma frequency, or in frequency, that's related to these underlying plasma physics parameters. Now, the interesting thing is, if we run our calibrator regularly, what we're going to do is we're going to trace out this impedance, because our calibrator tells us how well we match the antenna. And so all of a sudden, we actually have a plasma sensor in this frequency range. And we should be able to fit and measure a lot of the interesting plasma parameters if we run in this type of operational mode. We didn't promise that to NASA. That's going to be maybe the next mission that we promise that. But we're going to collect this data, and we're going to be able to fit in and analyze it. And we already know that it's going to be a very interesting plasma sensor. One of the reasons it's interesting, it's a plasma vector sensor, and I get direction of arrival of the plasma wave K vectors. So now I can tell whether I'm seeing an electromagnetic wave or an electrostatic wave. I can tell whether I've got upgoing waves or downgoing waves or both. I can tell all kinds of interesting things in terms of the underlying plasma physics that simply measuring a time frequency spectrogram doesn't give me. All right, bus design, just to go through some of this pretty quickly. We went with nanoavionics for our M6P bus. I'll talk to you offline if you want to know details. It's been good in some ways, and we've had some rough edges in others. We've managed to cram all this stuff in a 6U spacecraft. There's every little subsystem you'd imagine that you need. You've got your GPS, your flight computer, your payload computer, your magnetorquers, your X-band radio. And one of my jobs has been to try to make sure none of this interferes with everything. So one of the things your spacecraft can do is jam all your measurements in these low frequency ranges. And we have, from prior to bus selection, we've been using an experimental measurement program to quantify performance levels, quantify noise levels, and then design shielding and filtering, prove the shielding and filtering meets those levels, and then integrate it together into something where the whole combination doesn't jam itself in terms of emitting radio signals that make it impossible to see what we want. We've done pretty well so far with that. The only way to do it perfectly would be for us to design our own bus, and that's another project. This would be too much for this. This is the flight model hardware. NanoAvionics builds all this in Lithuania. So there's a couple pictures of the same thing here, but these are, this is the unfolded solar panels. You can actually see the UHF antennas up here. GPS antenna is there. There's a patch antenna for X-band up there. You can see there's two spacecrafts and their jigs, and we're expecting these to show up. They were supposed to show up in September. We're expecting them now in December, and we're going to get those at Haystack. The integration of the payload components isn't being done by Nanoavionics. We're doing this at MIT Haystack Observatory. If we had been really a lot smarter, we would have figured out a way to design this spacecraft so like the bus was the bottom two U, or the bottom U, a couple U across, and we had the rest. And that would have been really, really, really smart. And it turns out that we're very integrated physically. And so the only way for us to get everything in there is to do it ourselves. Fortunately, we got a good team of people. The other payload I didn't talk about, I'm going to talk a little bit about payloads. This is the awesome sensor package or auxiliary sensor package. This is actually student built. It's got 2 magnetometers per unit. So there's magnetometers up here. There's also an engineering camera that's a Raspberry Pi camera. We have a Pi 0 there. It all gets put together in an enclosure. There's all the bus connectors. And then there's a bunch of stuff we're doing to try to control EMI. One of the last things I think we have to do is fix the ribbon cable that's in here. I think that's putting out too much EMI, especially for the magnetometer. But we've shot for about 100 nanotesla sensitivity on the magnetometers on each individual one, and we're better than that in the lab testing. There's actually 4 of these units per spacecraft, so we actually have some local gradiometry that can be done to kind of try to get rid of the local magnetic field variations. And the Pi camera, strangely enough, has flight heritage. Other people have flown it and done pretty well in orbit with it. And it's mostly for us as a fisheye to see that the antenna has deployed. We might get some nice, pretty pictures from orbit too. The other major component other than vector sensor antenna is the Aurora software radio. This is a custom radio that we built with MIT Lincoln Laboratory. Haystack's been doing all the signal processing. I've been writing a lot of the software for this. And this system, basically, we custom designed everything in it. We synchronized the regulators in the system to the clock. So all our electromagnetic emissions that we self-generate are synchronized and localized, and we know where they are. And we actually put them in between the channels of our polyphase filter bank that pulls out the channels that we record. And that allows us to null them out to some extent. The receiver is incredibly compact. It's got 6 channels that run at 50 million samples a second. We can record about 250 megabytes a second of data, either filtered or raw. It takes real-time spectrograms that it integrates up, and this thing underneath it has a chip-scale atomic clock for its time reference, so it's got an incredibly stable clock. And we do this all in about 15 to 18 watts operationally. At the high thermal end, that becomes about 20 watts under temperature. And so this radio is actually one of the things we're deriving from for our ground-based radios that we're going to use for ground-based sensing systems. But all of the stuff, it processes its data in real time. We downlink the spectrogram to the ground. We select interesting intervals. We tell it what to do to that in terms of signal processing. And then we get down very compressed and reduced data so that we don't actually overwhelm our telemetry system. And we do have X-band for telemetry, but even 25 megabits per second telemetry is still pretty limited. Mechanical design, there's a lot of thought that went into this, and kind of everything is EMI shielded, and then it's all inside another EMI shield. Every layer in here has filtering between the different layers so that noise and signals, that you don't want in there don't get in. There's been a lot of work on the thermal interfaces in order to get the heat off that signal processing card and get it out to the edges of things. And the good thing is we used automotive parts. The really good thing is we bought them all before the pandemic and before the automotive parts shortage. So we had everything to finish this. Right now, if you go online and try to buy these parts, you can't find many of them. So it's a little bit challenging that way. Analog front end, I'm not going to go through every board, but this is an example of one of the boards. This is the analog front end. So you can see all the different channels and mode formers, and it connects into the spacecraft RF system down here. There's actually a back plug that goes on. These are the antenna connectors. They come in on wires differentially, so we can bring them in over a more conventional connector. And this is actually a series of serial number data overlaid with the simulated data. And we actually are very, very close between the modeling and the measurements of the performance of the analog system. We have built-in calibrator that we control that's a comb and a nice noise diode generator that allows us to put energy into the system to calibrate it. Now, when this energy goes in here, it doesn't just go out this way. It goes out the antennas and radiates at low levels also. So we're looking to do some things where we send coded signals using the calibrator from one spacecraft to another, for example, to do propagation measurements. Let's see here. This is the signal processing card, just to give you an idea of the complexity of the boards we're building for this. This is, I think it was like 48 layers of circuit board internally in order to do all the routing and to get everything there. This is the signal processing chip. That analog front end plugs in at the top up there, and it all plugs into the backplane for it there. And this is actually a really compact and high performance radio. It's not something you can just go buy. Well, not without building it yourself like we did. The clock. This is a chip scale atomic clock. Now, this was actually one of my students, one of the graduate students working with me. This is one of his projects. And he actually met all the specs with this clock, which we're using a chip scale atomic clock from Microsemi. These are really wonderful pieces of technology. They're ultra stable in a very low power and temperature stable package is one of the key things. This allows us to generate different sample clock rates that go out. We also generate a power synchronization clock that goes to everything. So all our power regulators that would generate EMI are synchronized, but they're synchronized to incredible precision because of that atomic clock. And so we do have crystals as backups and a bus PPS as backup, but underneath it, this has been quite successful, and it's been a nice project. Just to show some of the phase noise and performance of this clock. So we have kind of our FM units and our specs that we wanted to achieve. Allen deviation is kind of how the clock varies relative to itself randomly. There's jitter, which is how much the clock is fuzzing back and forth. There's phase noise, which is kind of another measure of jitter, but broken out by frequency. And then there's the drift over longer periods of how far over a given amount of time does the one clock drift from another clock if you have two of them. And so we measured all these things in the lab and against a hydrogen maser. And what we found is we're about 15 dB better on Allen deviation, sans thermal variations in orbit. So that's one of the things that's going to need that margin. The jitter is about 4 dB better, the phase noise 16 dB, and the drift is about 5 dB. But the key thing is that this clocking is absolutely fundamental to the data acquisition for interferometry. Because if the clocks are going all over, the data acquisition is going all over, and then all of a sudden these two platforms, you can't compare the data between them. All right. So this is great. We've actually been able to quantitatively achieve the metrics we set for the interferometry. And it corresponds to error bars on the interferometry for angular resolution that are kind of an order of magnitude better than we expect to achieve. So you're trying to set things so that the systematic errors and the random errors in the system are small enough compared to what you think your measurement errors are going to be, that they're not big contributors. Thermal analysis, I mentioned, we've done a lot of board level and enclosure level analysis to try to get the heat out of this. It turns out that our original power envelope we thought this was going to take was 35 watts, and our signal processing guys got it into 20 watts. So I was, and 15 for most of the operation. So I was like, we ended up like 30% under our power budget. So the thermals, we did a lot of work on it and they work really well. And now things are going to run cooler than we thought. So that means we actually just run them more, because we're going to turn on and run and take data and turn off. And now we'll be able to do more on time if we want to. There's two contact faces, although one of them is coupled to a thermal radiator to space. And that's where most of the energy goes on the system. Data, this is early data with a sinusoid and its harmonics. There's laboratory measurements kind of showing AM radio signals and actually a local ionoson. A lot of the fuzzy stuff in the spectrograms on the right are actually RFI from the fans in the clean room. So the fans, when I first saw this, I was like, oh, is this thing broken? What's wrong? And then I got into looking at it, and I went in with the radios and antennas, and I went up to the clean room fans, and I said, oh, there's the signature. And I bring it right down to the lab bench, and it looked exactly like this. I was like really stunned. So Aurora is this incredibly sensitive radio that finds all the RFI in the lab, which is good. We want a sensitive radio that when we put it in space in a quiet environment, will do well. Magnetometer performance, I said I mentioned this. what we found is the camera makes the magnetometer worse, and it's because that ribbon cable up to the camera, they built it with a big current loop where the signal and the energy goes out and back. So it's actually, every time you turn on the camera, the signals are making the magnetometers see the B field from the camera. But it turns out we're under 100 nanotesla on all our axes. The two cameras are actually set differently in the spacecraft, so we get some diversity spatially. So I think when we do joint analysis of the camera, of the magnetometers with the cameras off, we actually should do way better than 100 nanotesla. And I know Mark Moldwin at Michigan has done some stuff like this where they also looked at the current draw of the various power subsystems and were able to model and predict its effect on the magnetometers, and they got another order of magnitude better than this. So you can do better than this, but for a student-built magnetometer, this is pretty good, and it's going to let us see auroral current systems as we go through them. So it gives us another independent locality of we're in an energized region. The other thing we need the magnetic field for, though, is we're looking at a given direction of propagation of the radio wave. We want to know what the local magnetic field at the spacecraft is, where we're receiving that radio wave, because it's important for how that radio wave got refracted to us. And the ionospheric models give you kind of bulk background, or the magnetic field models like IGRF give you this bulk background field that's an average field that's been fitted. And it doesn't have a lot of the high frequencies components or variations that you see in real data. And so this is going to be a very important thing for us understanding the propagation vectors and essentially orienting that electromagnetic vector sensor relative to the magnetic field so we can interpret the data. Electromagnetic interference. I mentioned a campaign to deal with this. These are some measurements that we took of the bus early on, and we've gone through every single piece of the spacecraft. We specified shielding. They added shielding into the spacecraft. We added special filtering between the solar panels and the EPS of the spacecraft to keep energy from radiating out the solar panels into the antenna. And so, usually we've been shooting for 70 dB near 400 kilohertz up to about 40 dB, down to 40 dB of conductive and radiative isolation out to 15 megahertz. And so far as we've put things together, everything is real quiet. In fact, the data, some of the data I took earlier was in the spacecraft, and you weren't seeing the spacecraft bus, except if I zoomed in on certain frequencies, I could say, oh, that's the I2C telemetry readout that the spacecraft's doing. But the bus is by no means the predominant noise source right now. In fact, the lab is the predominant noise source in most of our testing. So where are we going with AERO-VISTA? The bigger picture view is, yes, we're going to have a wonderful mission to explore the radio aurora, and we're going to just hopefully make some images and get a lot of data, and of course write a lot of papers because we like to do that being academics. And we'll learn about plasma physics of the auroral kilometric radiation, as well as the zoo of phenomena we know about. We can always hope we'll find something new for the zoo, some new plasma physics that we don't understand or haven't seen before and can study. But the bigger picture when you step back is that this is a technological step towards radio interferometry constellations, operating first at low frequency for interferometry. And later, it's very hard even to do this at these low frequencies with the clocks we've got and the systems we can build, but pushing up to higher frequencies. Now, it turns out that the Earth is not the only planet that emits radio waves in these lower frequency range. Jupiter has Jovian kilometric radiation. Saturn actually emits down in the few hundred kilohertz range. Uranus, Neptune, all have signals at that low frequency end. Planets around other stars also emit. Our sun emits radio signals, solar radio bursts. So there's an incredible world out there that we don't see on the ground very well because the Earth's ionosphere acts to shield us. So by being able to put our electromagnetic vector sensor platforms on small spacecraft, and then down the road make many more of these and put them someplace, not too noisy, not too far away, say geostationary orbit, we can imagine having large constellations of hundreds or thousands of sensors. And that starts to be something that allows us to go after exoplanets. We can start to look for hot Jupiters around other stars that are emitting radio waves, localize them to the star where their brightness of the hot Jupiter is predicted to be about the same as the star. So instead of like a tremendous dynamic range problem of a very bright thing and a very dim thing, you have two equally bright things you have to separate. And so this is very exciting. You can explore a lot of things using in a non-thermal plasma environment around a planet or a star that you can't get at in other ways. The frequencies you see tell you a lot about the magnetic field. They tell you a lot about the plasma that's generating those frequencies. The variations in the frequencies you see can tell you things about like the orbits of moons around Jupiter. You can actually see very nicely the modulation effects on Jovian calorimetric radiation of Jupiter's moons, like Io, for example, in particular. So it's very exciting. This is an example from one of our teammates, Mary Knapp, who's our assistant PM and PI. She worked on the Asteria mission, which was an optical mission to look at exoplanets. And this is actually 55 Cancri and then 53 Cancri. And the bright dots in the center are the stars. And then it's the point spread function is around that. And this is an image plane, a pixel image plane view with intensity. They actually tracked the variation of 55 Cancri to see a known exoplanet vary with a small spacecraft optically. So you can imagine a constellation of radio sensors gives us the radio equivalent of these kinds of optical cameras and observations, but it gives us all this extra insight because of the nature of the measurement that we can make. So that's the exciting future with this. In summary, AERO-VISTA is going to observe the Earth's radio aurora. It's got unprecedented direction finding, resolution, and imaging capability in such a small spacecraft. We're going to address fundamental questions about radio aurora generation and propagation, and we're going to demonstrate vector sensor interferometry in space on orbit as a technology. And the future is going to be radio interferometry constellations. We're going to have about a year delay now, so we think our delivery launch provider is no earlier than about Q2 2024, and then hopefully it won't be too long after that we're up on orbit for likely a year-long mission roughly with these spacecraft. And there will be more. There's already interest from a lot of people. And so thank you very much.
So it's a 3:05. We will just take a couple of short questions. Anyone? Or anyone from the online audience?
So these clocks you're flying, so this will replace GPS for the time?
So we use GPS for epoch synchronization. We don't use it to stabilize the individual radio clocks. One of the reasons is GPS on orbit can be kind of intermittent sometimes. The underlying clock technology here is good enough for use up to a few hundred megahertz for interferometry. There's a new generation of these coming along that'll be as good as hydrogen masers. And they're going to open up things to much higher frequency ranges. At Haystack, we're interested not just at the low frequency end for space interferometry, but also all the way up to the millimeter wave for very long baseline interferometry, in particular looking for black hole signatures and event horizons. But to do that high technology, super high frequency thing, we felt it was good to get experience doing things at what should be the easy end. And I gotta say, this is hard in many of its own ways. And the amount of stuff we're cramming into these spacecraft and the complexity of kind of a small constellation mission, at some level, I was telling Colin, our director, look, you can build a small instrument and get a little bit of money for it, and you still have to write the software, make the instrument work, calibrate it, or you can write a very expensive instrument and you have to write the software and calibrate it and make the instrument work. And you're doing all the same amount of work, but maybe if you're doing the constellation, you're replicating many more copies. And some of that scales linearly, but a lot of the work, the small missions are absolutely as hard in many cases as the bigger missions, but on a much tighter budget. And that's one of the things we ran into is our initial scoping of this, we thought we could do it in 3U. Not at the sensitivity levels that the science requirements came in at. We could do something in 3U, but it wouldn't have looked like this, kind of high performance thing. The antenna, we thought, oh, mechanical engineers, make it pop out like a jack in the box, we're done. That has turned out to be a complex mechanical deployable that very few CubeSats have done stuff at that level. In fact, DARPA spent a lot of money with JPL and with some other follow-on corporations building similar sensors with just dipoles that just spooled out. And the first 3 of them all failed because of antenna problems. And several of them were self-jamming, where the rate bus interfered, and they finally got some that worked really, really well. So they had to work very hard. And they visited us at one point, and we were talking about X problem, Y problem. They're like, oh, yes, we saw that. So yeah, so there's a lot that goes into this, but you know, the clocks are an enabler, and eventually we won't need GPS necessarily, except kind of for this epoch synchronization.
Another question?
Why did the vector sensor that looks like a ball, why was that so difficult to make and operate?
So it turns out there's a lot of common mode effects. So those dipoles being inside the loops influence the loop response and make it non-ideal. The loops being near the dipoles make the dipole response not ideal. The idea of a dipole that is also a loop goes back in the antenna literature, electromagnetics literature, to the 60s. And there was, I forgot, I could look the gentleman up for you, but he wrote a paper that said, hey, if you take and do the following circuit, you get a dipole. But if you also do the following, you get a loop out of the same antenna. Isn't that cool? And that sat there until, I don't know, 2010, when there were some people who were working for that AERO program who said, wait a second, why don't we do it this way? It'll get rid of all those common mode effects that we're seeing in the sensor we built that make it hard to work. There's other subtleties, it turns out. The first people who tried to do this literally took dipoles and loops, put them together, and the sensor didn't work. And they were like, oh, and they tried and tried and tried and it failed. Well, it turned out that on the ground, right, I have a ground plane under me often. That changes. I'm not a vector sensor with 3E and 3B in free space like we're going to be with AERO-VISTA. We're going to be, 400 kilometers. There'll be nothing around us. It really will look like loops and dipoles. You have a reflection in the ground plane. The moment you have that reflection, if you line the sensor up with the ground plane, you actually destroy your degrees of freedom, and the vector sensor doesn't have enough information to do much about angle of arrival. So it works very, very poorly. If you actually rotate your sensor relative to the ground plane, you break the ambiguities geometrically, and now it works properly. So one of the things we found when we built the Atom antenna, which was a differential design, we actually rotated it in order to fix that. And we found that all the things people were seeing that they were saying, oh, it doesn't work in this case, we could explain them purely in terms of the way the radio waves were propagating over the ground plane and the projection on the antennas. And so there's a lot of little subtleties that come into this. There's other interesting subtleties that we have to publish it, but we've kind of proven that the electromagnetic vector sensor is the best you can do in terms of measuring an electromagnetic wave at a narrow band and frequency at a single point in space. All right. There's a lot of questions about like how to do these on bigger scales or how to have more aperture, but this is about, for what we're doing, it's about the best one can do. And the best you can think of is to try to make it more precise in how you build it, for example.
Any questions from online audience?
Yeah.
Okay, then let's thank Frank again.
Thank you. It's a pleasure.